Okay guys, in this presentation I will talk about the multi-arm bandit problem, which can be considered as the simplest reinforcement learning problem. It does not have like the complete number of properties that we could think of when we talk about our reinforcement learning, but it has like the in essence like the main goal behind reinforcement learning. So here in the picture you can see a machine, a one-arm bandit machine, and the idea of these machines is that you pull the lever and you receive a prize. Sometimes you receive a prize, sometimes you don't receive a prize. So imagine a machine that has a number k of levers, and the goal would be to discover which lever gives you the largest amount of points or prizes. So the question would be, if you have this multi-arm bandit machine, what would be your strategy to discover which lever is the winning one? So that's the problem of a multi-arm bandit problem. So suppose that you have a machine with 4 levers. So each of the levers will be considered as an action. So action 1 will represent that you pull the lever 1. Action 2 represents the action of pulling the lever 2, and so on. So we have a 4-arm bandit machine, and suppose that each of these levers will have a different distribution, the way it gives prizes. In this case the prizes will be numbers, and we are going to call these prizes rewards. So in this example, the action 1 always gives you a reward of 8. Okay, so we will consider that the value of executing action 1 will be 8, because we expect to get a reward of 8 after pulling or executing action 1. So here in this notation we have Q star of 1, where 1 is the number of action, and Q is going to is a variable that will store the value of that action. You will see later on that the letter Q is always used for making reference to the value of a specific action. Okay, so in the case of lever 2, action 2, there's a special distribution in which this lever gives the rewards. So here 88% of the time the reward is 0, and 12% of the time it gives a prize or a reward of 100. So if we were to calculate what is the most probable reward, we just need to apply probabilities to calculate what would be the expected value for action 2 in this way. The action 3 gives you values or rewards randomly generated between -10 and 35, and this is equiprobable. So you have the same probability of getting any of the numbers in this interval, -10 to 35. So in this case maybe the most expected number would be something in the middle, something like the average of these numbers. And you will see that the average is very important in reinforcement learning, and many of the learning rules can be derived from the idea that computing the average of the rewards is a good idea, like in this case. And action 4 has a strange distribution. 1/3 of the times it will give you a reward of 0. Another third of the time it will give you a 20 as a reward, and the remaining third of the times you will receive a reward in this set that contains 8, 9 up to 18. So again, if we try to predict what is the most probable reward, you will get something maybe here, something like close to the mean of these rewards. So imagine that these machines, or this machine with 4 levers, has this distribution function in which it gives you the prices, but of course you don't know these distributions. So what would you do to maximize the rewards that you will get when you play with this machine? So there could be many strategies that we can think of. Like for example, maybe you can say, okay, I will play 10 times action 1, 10 times action 2, 10 times action 3, and 10 times action 4, and then I will just select the action that gave me the largest reward in any of these 40 actions that I played. Or maybe you would say, I will select randomly 10 of these actions, 10 of these 4 possible actions, and then I will select the one that gave me the largest reward, and then I will play only this one. So everybody can think of different strategies. So the idea here is, what would be an optimal strategy to do this? So on each of an infinite sequence of time steps, so t will be the time 1, 2, 3, so on, you need to choose an action which we will note as AT, the action executed in time step t, and you need to choose this action out of k possible actions. After you select this action and you execute it, you will receive a real valued reward RT. So you will get a number, a real number, that will be the reward, and we will make reference to that reward as RT, the reward you obtain in time t. Okay, so this is the game of the K-arm bandit problem. Then the reward depends only on the action taken. It is identically and independently distributed. So we are assuming here that each time you pull the lever, or you select an action in this machine, the reward that you will get is independent of previous rewards, and the way or the function behind the machine that generated this reward is identical from one play to the next play. So this is the IID framework. So the Q star of some action A can be approximated by computing the expectation of the reward that you will get in time t, given that the action that you perform in time t is action small a, and this is for all a in the set containing our k possible actions. So here we're saying we are going to estimate this q star for every action. In this case we have k actions, so we will have a q value for each of our k actions, and this value will be the estimation of the reward that you expect to gain when you execute that action. These true values are unknown, so we ignore the distribution and what is the true value for each of these k actions. So the distribution is unknown. However, your goal is to maximize these rewards that you will get in the long run. Okay, so we want to maximize the total reward as you play with this machine. So the strategy, a very general strategy, is that you must try two different kinds of actions. You must try actions which are called exploration actions to try to learn what is the distribution behind each of the actions. So you need to play actions just to learn what kind of rewards you are going to get. And also you need to play actions in order to exploit or take advantage of the information that you have already gathered through the exploration actions. So when you perform an action because you know that that action is currently, according to your estimations, the best one, we say that you are exploiting your information, your knowledge. And when you execute an action just to learn about the rewards that that action can give you, we say that you are exploring the action space. Okay, so the strategies start to develop based on this idea of exploring and exploiting. So we always talk in reinforcement learning about the exploration-exploitation trade-off. Suppose you form estimates, big Q, and this Q approximates the Q star of the action. Okay, so this Q star, we will assume that these are the true values, which we ignore, and we will try to estimate these values, and that estimation we will call Q, big Q. One of the very basic strategies to approach this exploration-exploitation dilemma is the greedy action, the greedy policy. And this greedy action means, given your current estimates of the Q values for all the actions, a greedy action will be selecting the action that has the maximum Q value at present time, at time t. Okay, so whenever we say you select a greedy action, what you need to do is to look all the Q values of the actions, and you will select the action with the largest Q. The greedy policy, there's a Epsilon-greedy policy that is like the basic idea in this trade-off between exploration and exploitation, which uses this greedy action. But in Epsilon-greedy, as you will see, Sometimes you will perform an exploratory action with some probability epsilon, and with some probability 1 minus epsilon you will perform this greedy action. So when you select and execute the action, which is at that moment considered the greedy action, we say we are exploiting the knowledge we have. And whenever you execute an action which is not the action that is considered the greedy action at that moment, then we say we are exploring. And this is the way to balance this trade-off between exploitation and exploration, defined by this way to select a greedy action. So you can't do both at the same time, of course, but you need to intertwine the execution of both kinds of actions. You cannot just do exploitation, because initially you don't have information about that, about the values of the actions. So you need to explore, but you cannot also just explore, because then you are not maximizing, you are just randomly selecting actions. So you need to explore and exploit. You can never stop exploring, but maybe you should explore less with time, or maybe not. Why they say maybe not? It will depend on the kind of environment you are working on. Suppose that this Bandit machine is a stationary environment. This means stationary means that the distributions that are working behind this machine, these distributions are static, so they are not changing with time. So if that is the situation, if the problem is stationary, then it makes sense to reduce the amount of exploration with time. So at some point you have explored enough, and you have discovered which is the best action. So then after that you just need to keep trying or playing the best action, because you know that the distributions of the rewards are not going to change. But if the distributions change with time, so suppose that after some random number of plays, the distributions of the rewards change, then this is a non-stationary problem, and in that kind of problem it is not a good idea to reduce exploration. So you need to keep a good amount of exploration all the time, because all the time the prices, the rewards are changing, the distribution of rewards are changing. So and this is a problem that we will analyze in other slides when we talk about the specific algorithms to maximize this reward as you play with a K-ARM Bandit machine. So it is important to notice that we need to do exploration and do exploitation, and we need to consider the greedy action in this strategy. So methods that learn action value estimates and nothing else, these are called action value methods, and this is the case that we have been describing now. Like, you need to discover what is the reward that you expect to gain for each of the actions. Later you will see that you can define also values over states, not over actions, and those are called state value actions. But in this case we first talk about action value methods. So one idea would be simply to compute the average. Like, for example, suppose that we're talking about action 1. What you can do, and this is what this expression is telling you is simply compute the average of the rewards that you got after executing action A. So this formula is what they are saying. Just sum all the rewards that you get with action A and divide that sum over the number of times that you have executed that action. Okay? It's just an average for each of the actions. In this formula, this 1 can be considered as a function that will output 1 if the action that you selected in time I was action A. So it's a fancy way to say compute an average of the rewards that you will get for each of the actions. So this sample average, because you need to average the samples that you generate, converts to the true values if the action is taken an infinite number of times. So if the number of times that you execute that action approaches infinity, in the limit, then your estimation, this big Q, will be exactly the true value of that action. So of course this is in the infinity. So this is Epsilon-greedy, the strategy I was telling you about. In Epsilon-greedy, in greedy actions selection you always exploit. In Epsilon-greedy you are usually greedy, but with probability epsilon you instead pick an action at random, possibly the greedy action again. Okay, so this is perhaps the simplest way to balance exploration and exploitation. And even though the idea is simple, it works very well in practical terms, and it is easy to extend to more complicated reinforcement learning problems. You will see that there are some other ways to select actions. Let's say more smarter ways to select action, let's say, because these methods consider more information than Epsilon-greedy, but the problem with those methods is that they are difficult to scale, to modify, in order to be applied in more difficult problems. So that's why Epsilon-greedy is by far the most popular action selection strategy when you program or you apply reinforcement learning. So this is a action selection policy, very, very common one, Epsilon-greedy. And this is the algorithm that you can implement to solve the K-arm bandit problem. In this algorithm, you initialize the values and the counter of how many times you have executed an action. So from A equals 1 to K, which is the total number of actions, you will have an array where you will store initially the Q values. Since we don't know anything about those actions, we will give a initial Q value of 0 to all of the actions, and N will be a counter how many times you have executed action A. So we initialize it also with 0, and then you need to repeat forever or up to some number of training episodes the next steps. First, you select the action that you want to execute. We will follow the Epsilon-greedy strategy for action selection, and then you need to give a value to epsilon. Epsilon is it's a probability, it's the exploration probability. So with probability 1 minus epsilon, you will select the greedy action. So you will check in your array containing the Q values which of the actions contains the largest Q. If you are applying this the very first time, all of the actions will have a Q value of 0. So to break this tie, we simply select a random action. So if many of the actions have the same largest Q value, it doesn't make any difference if you select any or the other. So you just select a random action among these actions with the largest maximum. Well, that is with probability 1 minus epsilon. With probability epsilon, then you will select a random action and consider that this random action could be even the greedy action. So once you have selected an action following Epsilon-greedy, you apply that action, you execute that action. Here we call this the function, we call the Bandit function, and the Bandit function is going to answer you to respond with a reward R. After that, you move the counter for action A. You will say, okay, we will add 1 because we have executed action A one more time, and then we update the average of the Q values, of the reward values, and this is an incremental way to compute an average. If you don't want to compute this incrementally, what you would need to do is to keep in memory all the rewards that you get after executing each of the actions, and every time you execute an action one more time, you need to get the most recent reward of that action, and you need to access your memory to check the other rewards that you got before with that same action and recompute the average. So that is not very efficient. So the best way is to apply this incremental rule to keep track of the average of the rewards that you will get for every action. Here this is simply 1 over the number of times that you have executed action A, and this is a subtraction of the current reward that you get minus the current Q value that you have stored in your array for A. So this is like the very basic algorithm for solving the Bandit problem with K arms. And even though this is very simple, you will see later in the algorithms, in the more sophisticated algorithms, that the idea behind those algorithms is very similar to this one. That's why it is important to understand each of the elements behind this problem and the main algorithm for solving the Bandit problem.